Chemistry 3111. Let's take a look at question 11.7. You see that in this first question, we have a change in the carbon skeleton. We're going from a total of 5 carbons to 8 carbons. So we're adding 3 carbons. Now, what I notice is that we have the triple bond at the end of the molecule here. We have a double bond here. We know how to convert a triple to a cis double bond by treatment with Lindlar's catalyst and hydrogen. And then we're also adding 1, 2, 3 carbons to the molecule. So that means if we were to take this starting alkyne and treat it with sodium amide, followed by propyl iodide. So here we go, propyl iodide. That would give us this compound. So if we have 1, 2, try to clean this up here, 2, 3. I'll move this over a little bit. There we go. Then we add 1, 2, 3 carbons like this. So now we've added 3 carbons. So we have a total of 8 carbons in the molecule. Now all we have to do is take that triple bond and reduce it to a cis alkene. So hopefully you remember how to do that. We're going to take it and we're going to treat it with hydrogen and Lindlar's catalyst, which is a poisoned catalyst. Sometimes you hear it called a poisoned catalyst, like that. Here we go. Well, let's move on to the next one. So in the next one, we're starting with 6 carbons in this alkene that the author seems a little obsessed with. And then we're going to end up making a molecule with 9 carbons. So, oops. There we go. Looks something like this. There we go. That looks a little better. Anyhow, well, how are we going to do this? This one is a little trickier, in my opinion. A little trickier. Again, we're starting out with 6 carbons, and we're ending up with a molecule that has a total of 9 carbons. So the key in this one is, again, if you can assume that you have small alkanides like this. Like, let's say you had sodium, let's say you had this sodium anion here, this sodium acetyl or sodium alkanide. If you had that, then all you'd have to do is an anti-Markovnikov addition. Sorry, I'm getting tired here. Anti-Markovnikov addition of HBr across that double bond, which gives you a primary alkyl halide, and then you could treat that with this compound, right? And that ion, I should say, and that would do an SN2, wouldn't it? Right? You would end up doing this SN2 like this, which would give you this compound. So let me make sure I don't make any mistakes here. And we have like this. You'd end up with this guy. Sorry, I can draw it a little better than that. It's kind of hard to draw straight lines on the tablet, I find. There we go, like that. And then if we want to reduce this to a trans alkene, we would treat that with sodium and liquid ammonia. So sodium and liquid ammonia. That's a total of what? 3 steps, right? 3 steps total. All right. Well, let's take a look at the last one. The last one, we're starting out with this molecule. So we have this double bond like that. And then we're taking it and we're converting it into a terminal alkyne. It looks like this. Okay, so we're starting out with 5 carbons in our molecule, and we're ending up with 7 carbons in a molecule. And this one is a good example. You can see that as long as if you had this compound, and if you had the bromine over here, then all you'd have to do is treat this with sodium acetylide, right? And you'd end up with the desired compound. So then the question becomes, how do I get from here to here? Well, if I did an anti-Markovnikov addition of HBr first, HBr and peroxides, I'd end up with this molecule. So this would be 2-bromo-3-methyl-butane. And then I can treat that with potassium T-butoxide, so that I end up making the Hoffman alkene. There we go, like that. And then if I want to convert it to that primary alkyl bromide, I'm just going to do another anti-Markovnikov addition of HBr, which would give me this primary alkyl halide. And then the last step, I'm going to treat it with sodium acetylide. Put the lone pair and the negative charge here, right? Which is just going to do another SN2 like this to give us the final product like that. So I'm having a problem with my MacBook. Just give me a second here. All right. All right. Okay, good. There we go. Well, let's move on from there and let's take a look at some other concepts that we need to have mastered out of this chapter. So we just covered question 11.7. So we covered all three of those. Now let's talk about retrosynthetic analysis. And that's something that you saw me refer to in the last problem. Every once in a while, you saw me invoke this type of arrow where I went like this and I hit a double-lined arrow. That is a retrosynthesis arrow. This one here, retrosynthesis arrow. Man, struggling. There we go. So a retrosynthetic arrow. And that just means that we're thinking about the reaction in reverse. Retrosynthesis will come in even more handier, if you will, in organic chemistry too, because we look at so much more synthesis in this class. And so, you know, you can oftentimes just take one step backwards and say, well, what could I have as a precursor to my final product, let's say? And then you can kind of think about, you know, what would I need to affect that transformation? And then you can solve a lot of problems backwards. Let me show you what I mean. Let's say you wanted to do this reaction here, or this synthesis. You want to take this primary alcohol and you want to convert it into this alkyne. Well, it might not look that simple, you know, to look at it, you know, just at face value. But if you start with the alkyne and think, okay, well, how many ways do I know how to make an alkyne? Really, you've only got one thing at your disposal, right? If you think about this in terms of retrosynthesis, you'd have to have this molecule. If you had the vicinal dibromide, right, then you could just take that and treat it with excess sodium amide, right? And then you could treat it with water and you'd end up with that compound. Well, at least we've got one part figured out. And now we kind of are wondering, well, how do we get from here to here? Well, even if you can't solve that, it's no big deal, because what if you do another step retrosynthetically, right? Same type of idea. I know that the only way that I could make that vicinal dibromide would be to start it with this alkene, right? And I would treat that with bromine. Okay, now it's getting even simpler. Right now it's, how do we get from here to here? Well, that's, you know, the kind of approach that we want to take. So if we take a look at the scheme that they have here, we talk with the last step. We'd want to start with the vicinal dibromide. And for that, you'd treat it with excess sodium amide followed by water. And how would we make that alkene? Well, we could make that alkene starting with our primary alcohol, then treating it with toluene sulfonyl chloride, TSCl, and pyridine, which is just a benzene ring that has a nitrogen inside of it, like that. And then DBU, diazobicycloundecane, or diazobicyclononane, which is DBN. So we can treat it with one of those weak nucleophile strong bases to do the elimination reaction to give us the alkene. And there you have it. So then it becomes a total of what? 5 steps, which might not be as evident until you think about the reaction in terms of retrosynthesis. To be sure that your answer is correct, look at each reaction going forwards and be sure to double check it and check for stereochemistry and regioselectivity. All right, let's give question 11.9 a shot. I'm going to give you a couple seconds to try these ones, so I'll give you a minute or two. All right, so let's start with this one here. We're making a halohydrin. And for this one, you know, in terms of retrosynthesis, as long as we had 1-butene, if we had this alkene, right, we could take that and we could treat it with bromine and water, and we would end up forming the halohydrin. So then the question becomes, well, how do I get from here to here? Right, I have 2 carbons, and I need to end up with 4 carbons. Well, the only way that we know how to do that would be to treat the molecule first with sodium amide, followed by ethyl iodide, and that would give us 1-butyne. And if we want to convert that to 1-butene, we can either use sodium metal reduction in liquid ammonia, or we could use hydrogen in Lindlar's catalyst. Remember, cis or trans doesn't matter here. Hydrogenation is simpler than using sodium, which is a metal, which is kind of dangerous to mess around with. And there you have it, folks. Now we just treat it with bromine and water, and we've completed the synthesis just like that. Let's try another one. This is the second one that I had on that slide. So we're starting it with this compound. So this is 2,3-dimethylbutane. And if we want to convert that into a primary alcohol, this is another great example of how we could employ retrosynthesis to get ourselves going. Right? As long as we have this alkene, right? If we had that alkene, we could take that and we could do an anti-Markovnikov addition of water, right? We could treat it with borane and THF, and then we could treat it with hydrogen peroxide and sodium hydroxide, and that would do an anti-Markovnikov addition. So then the question becomes, well, how do I get from here to here? Well, hopefully you remember that the only possible reaction you can do with the first compound is to treat it with bromine and light or heat. So we'll put light, electromagnetic radiation, which would give us this compound, where we have the bromine on the most substituted carbon. Now, if I have 2 types of beta protons, I have this one that I have written in red, and I have this one written in blue. If I want to pull off the one in red to make the Hoffman alkene, what am I going to do? I'm going to treat it with a hindered base, like potassium T-butoxide, which is going to produce that alkene that I wanted to make from the beginning. There we go. Now I have the desired alkene, and now in the last step, I can treat this with borane and THF, followed by hydrogen peroxide and sodium hydroxide. And there you have it, anti-Markovnikov addition of water across that double bond to give us the primary alcohol. Let's try one more. So let's take a look at this one. We're starting out with this compound, which has a total of 5 carbons, and we want to make this alkyne. Here we have no changes in the carbon skeleton, do we? Right, no changes at all. But we know from retrosynthesis that the only way that we know how to make a triple bond like that, to make an alkyne, would be to start out with, or to the precursor to be this vicinal dibromide. Well, we also know that the only thing we can do with this molecule is to treat it with bromine and light or heat, which would give us this compound with our bromine on the most substituted carbon. Well, in order for me to make this compound, I would have to have this starting alkene. Then the question becomes, well, how do I get from this compound to this alkene? If I do an elimination using sodium methoxide, that ends up making this alkene. It's not the alkene that I want, but I'm closer to getting to that alkene, aren't I? Let me show you why. If I take that starting alkene, or this one that I have here, and I do an anti-Markovnikov addition of HBr, I end up with this molecule. And then I can do an elimination using potassium T-butoxide to make that alkene that I wanted. Right? Then I treat it with bromine, and then I do my double elimination, where I do excess sodium amide. Oops. Here we go. Excess sodium amide. And then in the last step, I treat it with water. Not hydronium, with water. Kind of a lengthy process, this one, isn't it? It's a total of 7 steps, right? You have 1, 2, 3, 4, 5, 6, and 7. 7 steps. It's pretty long synthesis. So that's a perfect example of, where you might get stuck. 7 steps is a lot of steps. But if you take it backwards, go backwards, and then you look at, what is the possibilities going forwards, oftentimes you can solve these kinds of problems in that way. Okay, so now we've solved question 11.9. I don't want to skip the section on green chemistry. It's a pretty important section, actually. Green chemistry just refers to chemists trying to find new ways to do syntheses so that they are less harmful to the environment. Years ago, chemists would just do whatever they could to get whatever molecule they wanted. But now we're finding that there's an environmental impact that results from just not really caring about how you do your chemistry. And so there are 4 guiding principles that scientists use nowadays to try to find ways to do reactions that are more green or less harmful to the environment. We want to prevent waste, right? If you have taken the organic chemistry 1 lab with me, maybe in the last semester, you see that we end up always having a waste bottle in the corner or one of the fume hoods that we throw waste into. How can we avoid having waste? Right, we want to use less hazardous substances. If you could do a Markovnikov addition with H3O plus versus mercuric acetate and water followed by sodium borohydride, right? Well, you want to avoid using mercury at all costs. So we're just trying to use reagents that have less harmful, or just reagents that are less harmful for the environment. Safer solvents, that's a big one, right? If you think about in the olden days, and I know that most of you are just learning organic chemistry, but in the olden days, chemists would do reactions in carbon tetrachloride and lots of chlorinated solvents, which are really harmful for the environment and harmful for the scientists that do the reactions. And so we're trying to find more ways to do reactions in water, which is actually not very easy in organic chemistry, but it's never a bad thing to do reactions in water when they work. And then maximize atom economy. Now, the concept of atom economy was developed by a chemist by the name of Barry Trost, and you can Google him if you want. He's a famous organic chemist. I think he won the Nobel Prize. And Barry Trost developed the whole idea of atom economy, and there's some calculations that go along with it that we don't look at in this class. However, it's just a way of being sure that all of the atoms that are in your reagents are incorporated into your final products. Let me show you what I mean. Here are 2 ways that we know how to make an alcohol. Okay, so we started with this alkene, and we want to do a Markovnikov addition of water. Well, we could either use oxymercuration, demercuration, or we could use an acid catalyzed hydration. You see that if we use oxymercuration, demercuration, most of the atoms end up in the waste bucket, right? The mercury, the oxygens from the acetate, the boron, and the 3 hydrogens, right? Everything ends up in the waste bucket except for the H2O. So that has a poor atom economy. There's a lot of atoms that end up in waste material. However, if we just use a little bit of H3O plus, right, the only thing that's going to go in the waste bucket would be the catalytic amount of hydrogen. Not that bad, is it? Right? So this is just one example of trying to choose more green reaction conditions that have a better atom economy. Other ways that we can improve our chemistry in terms of making it more environmentally friendly are to use catalysts, right? Rather than stoichiometric amounts of reagents. So things like hydrogenation using small amounts of palladium, platinum, and nickel. Energy efficiency is another one that I don't think about a lot, but if you have a reaction that you have to heat up to 100 degrees Celsius for, let's say, a day, you're going to use a lot less or a lot more electricity rather than if you did the reaction at room temperature for a day, right? And renewable feedstocks, if you can have a starting material that comes from, let's say, grains or corn, something that can be replenished quickly, as opposed to coming from the petroleum industry, being isolated from crude oil, which is not a renewable energy source. All right. The last section of chapter 11 deals with creating your own practice problems and just, organizing the reactions in your brain. And, there's kind of two sets of reactions. There's ones that move functional groups around, and then there's ones that change the carbon skeleton. I mean, all of my students that I've taught over the years, thousands of students, have developed their own ways of memorizing reactions and helping them to make sense for them. So you have to be, proactive in figuring out what works best for you. And so a lot of students hone and develop their studying skills when they take a class like organic chemistry, because it does involve some memorization as well as the application of the skills that or the reactions that you've memorized along the way. Designing your own synthesis problems, this is something you can do if you want to. I don't force my students to do this. I don't ask them to do this. I don't make them do it on a quiz or anything like that. But if you really wanted to make your own problems, if you've run out of problems, and I don't see how you could do that nowadays because you could always peruse the internet and look for more. But if you start with something that's really simple and then you just kind of do reactions on that small molecule, then you can just do it a few times and you could maybe trade problems with your friends. It's just an idea. Like, let's say you started with acetylene. You said, okay, well, if I treated that with these two reaction conditions, I end up making propine, and then I could take that propine and I could make it bigger and I could reduce it. And then you could kind of hand that to a friend and say, how did I come up with this? It's just an idea. Anyhow, again, I've never forced students to do it. And I don't know if many students have used this idea over the years, but I'm sure a few have along the way. Something that you're going to see a lot of in Chemistry 3111 is this, okay, especially once we get in a few chapters along the way. You're going to see a lot of synthesis problems where there's more than one way to affect the transformation. Here we have the anti-Markovnikov addition of water across this terminal alkene. Well, you could either do it using hydroboration oxidation, or you could just do an anti-Markovnikov addition of brom or HBr across the double bond and then displace it by an SN2, right, using hydroxide. And the answer is this, when students are like, which one's right? They're both right. There's nothing wrong with either of them. But in Chemistry 3111, what I'm going to be looking for are the shortest steps, okay? The ones having the fewest steps along the way. So what that means is, let's say you come up with an answer that's technically correct, and you use 13 steps, whereas, the problem can be solved in 4 steps. I would, generally speaking, say that's wrong to do the reaction or do the whole synthesis in 13 steps, right? That doesn't seem like very good or very green chemistry to me. And I know it probably doesn't seem like green chemistry to you. And you'd be 100% correct in assuming that. All right. And that covers everything from chapter 11.